Welcome to Lecture 7. We're now in the second half of Weather Prediction 2. During the first half, we focused on hurricane forecasting, tropical tips. We touched on mesovortices, hurricane history. So hopefully you found that interesting. That's my passion. That's what I truly love. So I try to share as much as I could on that. On the second half of the class, I'm going to try to make you as versatile as possible. I'm going to try to give you a whole broad range of topics from long-range forecasting to western weather to coastal weather with rip currents and water spouts and lake and sea breezes. So a good variety of topics that will finish out weather prediction 2. All right, so let's get started with long-range forecasting. We're going to be focusing on both ensembles and teleconnections. And this will be a longer lecture, but the great thing with DL, if you need a break, just hit pause. So it's not a big deal. If you want to break this up into sections, that is perfectly fine with me. So it's become more and more that you have a lot more pressure with that long-range forecasting. And what I mean by that is, as time has gone on, as now we're 2019, I'm seeing not just 7-day forecasts coming out, but 14-day forecasts. I've even seen 30-day forecasts. And as you know, as a forecaster, the further you go out, the more difficult it gets. If you remember Dr. Wax from Weather and Climate or Intro to Meteorology, he used to say all the time, anything over 3 days is magic, all right? Now, I think we can do a little bit better than magic once we get 3 days out. But it's difficult, okay? And with experience, you will get better at this. And this is something I love, and I feel like I've gotten pretty darn good at it. But again, I still get plenty wrong, just like anybody else. And the more you practice, the better you get. And really, like I've told you many, many times, you're really just trying to be less wrong than everyone else and less wrong than the computer models. If you can use certain tips that I've taught you in teleconnections and pattern recognition, it can help you at least fine-tune that forecast, make it a little bit better, okay? If you're doing a 7-day forecast and all the models are showing it being really warm, but the teleconnections and the pattern says there's going to be a big trough over you, why are you going to go really wrong with all the models? That's what I'm talking about with understanding pattern recognition, all right? So long-range forecast should not be based just on the average of guidance or a majority vote, even though it is useful to know if a particular model is an outlier. So what do I mean by that? Just because 9 out of 10 models say something's going to happen doesn't necessarily mean that's going to happen. Now, if you don't have any reason to go against it, then yes, I'd rather have the odds on my side. But even if 9 out of 10 said a certain thing, and the one that was against all of them said a certain thing that made sense, I'm going with the 1 over 9, okay? So let me give you an example of that. Let's say you had blocking, a negative NAO, all right? Everything is backed up. It's like a big toll booth, right? Everything's backing up. Those troughs are digging further into the eastern U.S. And I looked at the long-range forecast, and the models were showing faster progression. Why would I go with faster progression just because the majority says that when I know because of the teleconnections and the pattern recognition that the pattern's not going to be faster, it's going to be slower. So in that circumstance, I don't care if it's 9 out of 10. The 1 makes more sense, okay? So that's just an example of that. Also, I see a lot of people will average them. Let's say you had 4 models that you were looking at, and 2 of them said a foot of snow, and 2 of them said, 6 inches of snow. Well, I'll see a lot of people just go, well, we'll just go with 9. I mean, maybe when you first are learning, you start off, that's not the worst thing you can do. It kind of minimalizes your error to a point. But I feel like you can do much better than that. And you can use these same teleconnections and tips and pattern recognition to help you decide, does 12 inches of snow make more sense? Or does 6 inches of snow make more sense, okay? And it's good to note outliers. Yes, a lot of times you do want to play the odds, but sometimes that outlier makes more sense than all the other models that are against it, okay? Can you determine why a model or model output is different? As you get better at this, you're going to be able to do that. You're going to look at a certain model, and you've been looking at it for years and years and years, and you're going to start noticing biases, okay? And I try to be careful not to tell you too many of the biases because while, yes, these biases apply in 2019, what about 10 years from now or 20 years from now? The models are constantly going to be updated and improved. So like the GFS bias, the problem with heat, and always trying to break down the ridge and having that right bias, which has worked for about 20 years, may not work 20 years down the road or may not even work 5 years down the road. The GFS is improving. They just recently updated it and it's now the GFS FV3. So they're going to just keep improving it. All right. So got to be careful about that. But still, hopefully you'll get to the point where you can look at the model and go, all right, I know this bias. I know it struggles with this. I'm going to be careful not to get tricked by this. Okay. And then you want to just look at the basics. Look at the surface, the satellite, the radar, water vapor, where the position of the trough and ridge is, what are your dew point temps, where is your rain at, all those things. How are the models initializing? Now, in general, if a model can't even get the current conditions right, I don't have much faith it's going to get even 24 hours down the road, right? And especially 7, 8, 9, 10 days down the road, okay? So does it guarantee if it initializes right away perfectly that it's going to be great down the road? No, but I'm going to feel a heck of a lot better with a model that got the current conditions, or at least, the next 6 to 12 hours better than a model that's completely off day one at initialization, okay? So with experience too, you're going to start seeing as a model handle the situation better during a current season. And then you're going to start seeing global biases. So what do I mean by that? Well, let's just go back to GFS, the bias with heat, breaking down the ridge too much. Well, if the Atlantic is in a warm AMO and we're running above normal with heat, do you think that bias is going to be more pronounced or do you think it's going to be less? So it has a bias. It's usually always present. But if the waters are warmer, that bias is probably going to be even worse, right? What I mean by that is it's going to struggle even more, okay? Now, if the Atlantic is cold, maybe that bias will not be as pronounced. So you're going to start to get to the point where you're going to understand model biases seasonally, and then how the teleconnections change will change those biases, okay? One model may have a more pronounced bias during El Nino versus La Nina, or during the cold BDO versus the warm PDO, or the cold AMO versus the warm AMO, those type of things. And look, it's going to take a while, all right? If you think you're going to learn all this stuff in one class, that's impossible. It took me years before I even started getting kind of comfortable with this, all right? I've been doing this pretty much every day for 20 years. It takes a long time. The good news, though, is I'm going to give you the foundation, right? You have to start somewhere, so you're going to get the foundation, and then with time, at least you'll know how to start and how to get going, and then with time, you'll get better at it, all right? So which model makes the most sense given what is going on elsewhere in the world, all right? So we talked about that. An example, like I was saying, be suspicious of faster timing when there's blocking. If you have a negative NEO and there's blocking, and it's been present for a long time, especially during the winter time, why am I going to go with a faster timing when there's a toll booth, everything's being backed up, right? It's almost like traffic, right? So the teleconnections are going to really help you with this, all right? And the good news with the tropical tips and tropical forecasts, it introduced many of these teleconnections. So as we go through them, you're already going to have an idea what they do. We're just going to go more in depth and just try to give you a little bit more background behind it. So let's move on to ensembles, all right? So an ensemble is a collection of 2 or more forecasts that are valid for the same time period, okay? So in reality, if you're watching your local TV Mets and both of them are forecasting, let's say, where I live in Starkville, both of them are forecasting for Starkville on tomorrow, that's an ensemble, all right? 2 or more forecasts that are valid for the same place, same time, okay? Ensembles allow for an estimate of the uncertainty of a particular forecast, okay? Again, it goes back into the odds, all right? So not to over confuse you here, but there's a big difference between the operational, let's just stick with the European, all right? The operational European is not the same as the ensembles for the European, okay? So the operational European is run at its best resolution, all right? So the best model physics, the best, the strongest computers, the best initial conditions, all this are in the operational European. The ensemble, while still good, is not going to run at that same level. Why? Well, with the European, you're running it 51 times, okay? So imagine the computer power it would take to run 51 times at the same level it does the operational. The resolution is getting unbelievable on these global models, even with these operational models. All right, so you could pull up the Euro at 9 kilometers, which 20 years ago, if you told me a global model would be 9 kilometers, I probably would have laughed at you. All right, so and it's just going to get better. But my point is, while it's improving rapidly and our computers are just getting more and more powerful, the Europeans or the people putting out these forecasts or the people, running the numbers and all the people, putting the models together, all the DE and all the math and all that stuff, that's where that comes in. They can't run the ensemble at the same power as they're running the operational. That's the best way I can try to explain it, right? Operationals run at the highest power with the best conditions, with the best model physics and assumptions at the highest level they possibly can, okay? The ensembles, they can't do that because they're running it so many times. So what they do with the ensembles is they have a control run of the ensembles, right? So while that control run is not as good as the operational run in theory because it doesn't have the same computer power behind it, it's the best of the ensemble runs in theory. And what they do is they take that control run and then they tweak either the initial conditions or the model physics with the European 51 times, and they call these perturbations. And as they tweak the model physics 51 times, you get 51 different runs, which is the ensembles, okay? So operational, that's the top. And then in the ensemble world, you got the control, and then you got, each global model is different, but with the Europeans, I think it's 51 members that is run 51 times off the control, okay? So the control, which is the best of the ensemble, not quite as good as the operational, but still decent. And then they make perturbations where they either change the initial conditions or model physics, and they do that 51 times to give you the ensembles, okay? I'm not going to test you hardcore or anything like that. I'm just trying to explain that it's a little bit more complex than people think. And if you would like more information on that, you can definitely go to the actual European site, which I'm actually going to talk about on the next slide here, and get even more information. Or, the GFS, NSET, places like that. So when it comes to the GFS, they usually are, well, as far as I know still, even through 2019. Now, they just updated with the FV3, so maybe this will change. But when they are running their perturbations off the control run, they're changing the initial conditions, all right? So I don't know off the top of my head how many ensembles there are with the GFS, but let's just say, I don't know, we'll go 40, right? We're just picking a number. So when they take the control run of the GFS ensemble and they tweak that, they're tweaking the initial conditions 40 times to give you 40 different runs, okay? Whereas the CMC, that's Canadian, let's just use that same 40 number, they're going to tweak it off the control, but they're assuming that they have their initial conditions correct, but they're going to tweak the model physics and assumptions. All right, so the bottom line with that is some are going to tweak the initial conditions, some are going to tweak the model physics and assumptions. What's the good and the bad with that? Well, look at the GFS, right? Yes, that's great. It's tweaking initial conditions. It's trying to make sure it gets the initial conditions correct. But it's assuming that its model physics and assumptions are right. Well, we know with the GFS that's not the case, as it has a lot of issues, like I said, with heat and other things. So, yes, it's great. It's changing those initial conditions, but something that's fundamentally flawed is not being changed. So I would argue that makes their ensembles weaker in many ways, right? Whereas the Canadian is the opposite. It's assuming that it can get the initial conditions correct, but it needs to update those model physics and assumptions 40 times in order to get a better output, right? Well, the problem with that is if they're not getting initial conditions right, then even if their model physics are decent or pretty good, there's going to be problems, right? So what would be the best? The best would be a combo of both. So why don't all these different global models do that? Again, it goes back to computer power, right? There's only so much you can do to run these things, every 6 hours, right? So, if you want the 0, 6, 12, 18Z run, if you go back to the 40s and 50s, these mathematicians could actually have done what these computers are doing today. The problem is it would take them days and days to get this stuff done. So you could have these mathematicians in the 40s and 50s that knew the equations and could do the equations, but by the time they were done, what they were working on is 48 hours old. So that's the issue. It all has to do with computer power. As computer power increases, this will get better. You'll start to see more and more combine this, and the European is really kind of on, I don't want to say the cutting edge, but it's on the forefront of really doing this. And they're starting to, they've always messed with the initial conditions, but now they're starting to kind of change some of the model physics and assumptions, which to me makes their ensembles superior, at least at this point. Okay. So when we talk about ensembles, again, it's just a collection of two or more forecasts that are valid for the same time period. When was that term first used? Well, there could be some argument here, but what I've always read and I always heard was the first time the term ensemble was used was during the D-Day forecast, which recently is 70, they had the 75-year-old anniversary not too long ago. And look, we all have pressure forecasts. I'm sure all of you have had situations with tornadoes or hurricanes or heavy snow or wherever, or whatever I should say, where it was a lot of stress and pressure. But can you imagine that forecast when you're involving tens of thousands of people invading a country where their life depends on your forecast? And what was so tricky about that forecast is they're coming across, the English Channel coming over towards France, and they wanted some cloud cover and they wanted some poor conditions so the Germans couldn't just see them from miles and miles away and pick them off. They wanted them to have some cover. But at the same time, it's tricky. If it was too much rough conditions, then a lot of those, I don't know what the name of those ships or boat, the little smaller ones that the Marines were in that were coming in. I don't know the name of them. But if the water was too rough, they would have sank and never would have even made it there. All right. So that was such a fine line, such a pressure-packed forecast. And that was the first time the term ensembles has been used. I'm sure ensemble forecasts existed before that, but that was the first time the term was used. And from a pressure standpoint, it doesn't really get much harder than D-Day. So how does that's the European ECMWF produce an ensemble forecast? This is straight from their site. It produces 51 forecasts. One of these is known as the control forecast. All right, so I talked about that. The control is the best. That's the one that's going to have the best resolution, model physics, initial conditions. That's the one that's going to have in theory, the superior output, right? So what they do is they take that, with their best, again, this one is known as the control and it's produced with the best available data and unperturbed models, okay? Then they take that and the other 50 are each produced with slight perturbations of initial conditions of the models, okay? And of the models. So not just with the European initial conditions. There's still primarily more on that, but they're starting now to tweak the model physics as well as the computer power is getting stronger. They're able to really make this even stronger and better. All right. So taken together, the forecasts become the ensemble, which shows the range of possibility outcomes and likelihood of their occurrence. So, we talked about kind of how they get the ensembles out, how, you got your operational, and then when you're ensembles, you got your control, and then your different perturbations from it. You understand the differences that some global models are going to tweak the initial conditions, some are the model physics, but it's best to tweak both. But it comes down to computer power. And, one other thing I want to add is the ensemble is just in a way to just give you more confidence, okay? And it's never going to guarantee anything, but if I'm looking at my forecast and I'm looking at all the operational runs, and then I look at let's say I look at the GFS operational and it matches up with the mean ensemble, and I look at the European operational and matches up with the mean ensembles, and so forth and so forth. Does that guarantee I'm going to be right? No. But I'm going to feel a lot better if the operational runs are matching up with the ensemble runs. Again, it's going back to the odds. Yes, you don't always assume that that's how it's going to work, but more times, I don't know what the percentage would be, but more times I'm going to feel better if the ensembles are matching up with my operational guidance, okay? If the operational guidance was completely different than ensembles, then I got to sit there and figure out which one makes more sense, and it makes it more difficult, Okay, so there's different ways to go about that. You have ensemble means, you have spaghetti plots, you have probability forecasts. So there's all sorts of ensemble type products out there. So this is from the Canadian, and this is looking at heights with upper level high and low pressure. This is that if you know the Deep South and you know heat and heat and humidity down here, that's the famous death ridge, as they would call it, the 594. But to keep this simple, where you see these blue, these are letters here. This is showing you where the ensembles are saying high pressure is present aloft, and where these red letters are is showing you where it's saying there's upper level low pressure. Okay, in this case, they really agree really well, right? So when you have agreement like that, doesn't guarantee it's going to be perfect, no, but it makes you feel better about your forecast. All right, here's another example of that. This is more towards the surface. This is high pressure and low pressure. Same thing. When you see them more clustered together and more compacted, I'm going to have a little bit more confidence. All right. This is just one of, I don't know, hundreds of examples of different types of products out there. Okay. This is more in the shorter range. You're seeing good agreement here. But as we go into the longer range, look at that. It just looks like a shotgun blast, right? And that happens a lot, especially when you get out to day 7, 8, 9, 10. So where people can get tricked on this, you see zonal flow. Well, I'll see a lot of people look at a 10-day forecast and they go, oh, well, zonal flow. That's what the ensembles are showing. Well, not necessarily. What it could be is half of the ensembles are showing a trough, half the ensembles are showing a ridge, and it's just, remember, this is the mean. The average looks like a zonal flow, right? That doesn't mean it's going to be zonal flow. Could it be? Sure. But it's more likely that it's going to be one or the other, right? So that's where you got to get into the pattern recognition and the teleconnections to help you decide, does a trough make more sense or does a ridge make more sense? And where people get trapped again is they see this and they go, oh, zonal flow, yeah, no big deal. Well, be careful. Again, that could be a trick. Here's spaghetti plots. I don't use these as much, but you do see these a lot kind of, in a little different form with hurricane, track forecasting, things like that. So there's all different types of forms of this. I think on this one, I can't remember exactly what this is looking at 582 decameters and 522 decameters. So it's just showing you heights and where these averages are occurring. And you see, in the shorter range, good agreement. As you go further out, it makes sense. You're going to have more disagreement. You're going to have more variance. All right. So at this point, I feel pretty confident of some sort of, upper level low somewhere off the West Coast here, right? Maybe you can't pinpoint the exact placement, but you feel confident it's present there, right? Whereas this, I'm not so sure now, right? So, it's a lot of some troughiness, some ridginess. So it gets difficult when you get further up, okay? And that's where you got to tie everything else into it. Probability forecast. This is off the Canadian. This is probability of 2 millimeters, not 2 meters, because that would be a ridiculous amount, but 2 millimeters of rain, which is about a tenth of an inch, showing you the probability of that. This is off the, I believe this is the Shref, I believe. I'm not 100% sure here. Yes, it is the Shref. This is showing the probability of at least a quarter inch of precipitation. You see the scales there. This is we talked about this, the short range ensemble, which is basically the ensembles for the NAM. All right, and then this is what I like using more. This is just showing your mean 500 millibar height placement, and I'm looking at, the likelihood of troughs and ridges being in certain places, right? Because look at us here, like here in Mississippi, right? Is this a cold pattern or warm pattern? This is a cold pattern. All right. What if you had a big ridge over you? It'd be a warmer pattern, right? Now, obviously, it depends on the time of year, but storminess versus clear skies, non-stormy conditions, right? When I look at the mean and I see good agreement, especially when you go further out, I feel pretty good about it. Now, obviously, we're only looking 48 hours out, but you see there's really good agreement. The ensembles, the European ensembles had a good agreement with a ridge in the west, a trough in the east, and then ridging kind of moving back off of New England into Canada, and then kind of has that negative NAO look to it, right? Okay. So let's look at that. That's the ensemble mean. So that's 51 members. That's the mean versus what? The control. Okay, so how did I get those different members? We took the control and then we ran perturbations off that control. Okay, so this is just the singular control run. This is all the perturbations put together. All right, so the mean is all of them together, and this is just a single control run here. Right, so at 48 hours, pretty good agreement. I really don't see much difference at all, but it's only 48 hours out, so it makes sense, right? Now let's go further in time. So if we look at 248 hours out or 10 days out, what is it showing? Still showing a big ridge in the west, big ridge over towards Greenland. That has that negative NAO look and a nice trough in the eastern U.S., right? That's what the ensemble mean shows. Whereas the control, it's similar, but it's definitely different, right? It still has a ridge in the west, and it still has a ridge off the North Atlantic, but you can see the placement is different, right? You can definitely see the differences, and you can also see with the control that the trough is not as pronounced. Now, does that mean the control's wrong and the mean's always going to win? No, but when I see, this isn't like horrible. Sometimes you'll see it way worse than this, but when I start to see differences, I start to get a little bit more concerned in the long range, and I want to look at more things, okay? You got to be careful because just because it agrees perfectly at day 10 doesn't guarantee you're going to be right. But in general, if the ensembles are agreeing with the operational run, I definitely feel better, okay? So here's a quick little event that happened in Starkville. It was really interesting. And it was something where we used ensembles and we used lots of different models to come up with a forecast that actually worked out really well. As you know, well, maybe you don't, but I'm sure you've heard and seen that down here in the deep south, when we get snow, it's a big deal. All right, you say snow down here, even an inch or two of snow, they're going to clear out all the stores. And I know if you're from the north, you're probably like, wow, I can't believe people, get so crazy over an inch or two of snow. Fair enough. But in fairness, there's no salt truss. There's no way to treat the roads. And look, I learned how to drive in the snow in D.C. I've driven in blizzards. I've driven in huge nor'easters. I don't care how great of a driver you are in the snow. If you're in roads that are completely iced over with no salt and no traction, it's really hard to drive, all right? So in fairness, that is something we do struggle with here. So this was a tricky event. And the GFS really wasn't showing much precipitation at all. Some of the runs, I mean, it started off with maybe like a few hundredths, maybe 5/100ths of an inch, and then it really got down to almost showing maybe a hundredth or an inch or less, right? So the Euro was showing much more. All the other models were showing much more, but the GFS was really insistent that we weren't going to get snow. So especially, in 2011, people were really hanging their hat on the GFS and really, I knew people that's all they looked at, GFS. So I saw a lot of people forecasting no snow. They're like, oh, we're not going to get snow. It's not going to happen. Well, thankfully, I'm one of those super weather nerds, and I want to look at as much as I possibly can. And I kind of was like, well, I don't know about that. I actually think the GFS is wrong. All right, so we'll break that down. And to the credit, the Weather Service did great on this. They really did well on this, okay? So the NAM was showing a much different situation. The NAM was showing more like at least a quarter to a half inch. And even at 10-to-1 ratios, down here in the south to get 2, 5, 6, 7 inches of snow maybe, that's a big deal, okay? That can cause a lot of problems. So GFS is showing basically no snow. NAM is showing maybe up to 6 inches of snow. All right, so as we got closer to the event, the GFS, you could see it went, it was a little bit wetter at the beginning, but then as we got closer to the event, it really dried out, and, Starkville is right about here. I mean, it's basically showing nothing, okay? But what was interesting, and this is where the ensembles can be helpful, was even though the operational was not showing any rain, the ensembles were showing rain. The ensemble means were showing a half inch of QPF. Now, it did fluctuate up and down, and it did kind of go down a little bit, but it was still showing minimum a quarter inch to a half inch, right? So I started thinking to myself, well, wait a minute. The GFS operational is showing basically nothing, but the ensembles are insistent that there's going to be precipitation, okay? So does that mean for sure the operational run is wrong? No, but it made me kind of hesitate. Something's up here. especially in the short term like that, to see such major differences, that's not overly normal, all right? Day 7, 8, 9, 10, big differences? Yeah, that's normal. 24 hours out, that's not really that normal, okay? So what I did is I started looking at the GFS, and I started, what people do a lot is they just pull up the QPF, and that's it. Well, I started looking at 300 and 500 and 700 and 850, and what I started noticing was, boy, it's showing a lot of rising motion. It's showing a lot of PVA. It's showing some warm air advection. It's showing a lot of uplift. So why, if the operational model is showing all this uplift, why is it going with no rain? Well, that tells me something's wrong with the operational run. It made me lean more towards the ensembles, especially when all the other models were showing the same thing. Okay? I know I told you at the beginning that don't always go with the majority, but this time I had a reason to go with the majority. I didn't just go, well, throwing the GFS out. I started looking at the GFS in detail and asking myself, this doesn't make sense. How could there be this much uplift and no precipitation? All right, it makes no sense. All right. And the Canadian was showing a whole bunch of precipitation, even more than the NAM. And again, to the credit of the National Weather Service in Jackson, they nailed this. The forecast would be fairly straightforward if not for the assistance by the GFS that the wave will dampen more than the model consensus suggests. The GFS continues to come in considerably drier than other guidance, including the GF ensemble. They saw that as well. The mean of the ensemble, they looked at the GEM, which is the Canadian, the UK Met, the SHREF, the NAM, the European. The European did trend a little bit drier, but it was still showing between a quarter and a half inch. I even looked at the Japanese model, and it was showing precipitation as well. Okay, so the overall consensus suggests that the entire area will see between a quarter and a half inch, and they did really well with that forecast. And again, be careful. When you just look at the GFS and it shows no rain, don't just assume. Remember, you're a lawyer in the courtroom, and you're trying to figure out where the person's lying. And in this case, the person is the model, okay? It's lying somewhere. Sometimes it might be just telling a little lie, and other times it's telling big lies. And in this case, it was telling big lies, all right? And when everything's showing lots of rising motion and the model's not showing precipitation, I'm going to be hesitant to trust that, especially when everything else, including the ensembles and the means and everything, is showing precipitation, all right? So this is a great example. We're just using common knowledge, not even anything that hardcore. I went 5 inches of snow. We had between 4 and 6 inches of snow here in Starkville. And again, it's a big deal down here. If you say no snow and it snowed 5 or 6 inches down here in the south, you're never going to hear the end of it, okay? Now, on the flip side, I took a risk. With me going 5 inches of snow, if it would not have snowed, I would have been absolutely ripped apart as well, all right? So you better be confident on this. And what's difficult down here in the south, you blow a snow forecast, you might not get another one for years. All right, so this one was tricky, but using those tips really helped out. And then they just continued talking about the other trend notes that the system was faster. That was another thing I didn't really talk about. Everything was showing faster timing except for the GFS, which was also wrong with precipitation. And that was a big factor for us here because the snow actually came in more towards 2, 3, 4 o'clock in the afternoon, which affected the drive home for many people. All right, so the timing was important as well, but the GFS was wrong on that as well. All right, so I know I've already talked a lot, but this is a good spot for a break. The good news with the second part of this, with the teleconnections, is we've talked a lot about this. So I don't have to read every single thing, and I can go through it a little bit quicker. So if you want to take a good, 5-10 minutes, or shoot, if you want to stop and pick it up tomorrow, that's fine. If you were going to take a break, this would be a good place to take a break. Okay, so let's continue with teleconnections. So what is a teleconnection? It's a linkage between weather patterns and changes occurring in widely separate regions of the globe. When I first started learning about this, like remember the Japan Trough Ridge teleconnection, or the NAO, or the SOI, or I'm going to teach you other ones, okay? When I first started learning about this, I not that I completely threw it out, but I was like, really? I just kind of had my doubts with it. But then when I started practicing with it, and it really helped me forecast, especially in the longer range, I started to really believe in it. Now, anything in weather, there's nothing that's perfect, but this is going to give you a big advantage, okay? It's only going to help you. So, when we talk about these, teleconnections, what's a big one that everyone talks about? El Nino or La Nina. And people were, especially in the late 90s, people were joking about riding the El Nino, where you have rain and drought and rain and drought. And, like I told you, no two are the same. It just depends on where you live, and it depends on the exact setup that is occurring, all right? The Pacific is a large body of water. It depends on where that warm water is located, all right? There's a lot of jokes on people blaming things on El Nino. I don't know if you remember the Chris Farley skit from Saturday Night Live, El Nino, pretty funny. If you've never seen that, look it up on YouTube. It's pretty hilarious. But you have one cartoon here. I think it's Dennis the Menace here. Who's responsible for this mess? El Nino. So let me get this straight. You're blaming these bad grades on what? El Nino. So you saw a lot of these jokes in the late 90s. And then in 97, the kid breaks the vase and he blames it on El Nino. In 98, he breaks the same vase, but this time it's La Nina's fault. All right. We've talked a lot about this. I don't need to go on a tangent on this again. But just because El Nino's present or La Nina's present doesn't mean it's always going to produce the same thing. All right. And that's kind of what these jokes are getting at. It's just broad brushing it and saying it's El Nino's fault or La Nina's fault is not really accurate. That's just a piece of a puzzle. It's an important piece, but there's so many other pieces to put together, all right? And I've talked a lot about that. So let's kind of go a little bit more in the background. Thankfully, you have a pretty good understanding about this, and I'll go through this pretty quick. All right, so ENSO and El Nino Southern Oscillation is termed for the coupled ocean-atmospheric interactions in the tropical Pacific. El Nino is characterized by warmer than normal SSTs, so sea surface temperatures, in the equatorial and tropical eastern Pacific. Now, again, we talked about this with Modoki. It doesn't always have to be in the eastern Pacific. It can be in the central Pacific. But I will call it the more typical El Nino will be in the eastern Pacific, all right? Fluctuations in sea surface temperature anomalies are due to changes in the strength of the trade winds, all right? So we talked about that a good bit. If you have weak trade winds, what are you going to have? You're going to have warmer waters. If you have the stronger trade winds, that's blowing that warmer water away, and then you get upwelling, okay? When the pressure measure, the way they get these, I'm going to show you SOI is the index they use to measure this. They measure pressure from Darwin, Australia, and they compare it to the pressure in Tahiti. Maybe we should all do a research project and go out to either one of these spots. I'd be down to do that and kind of research this in more depth. But in all seriousness, they look at Darwin, Australia, they look at Tahiti, and they look at the differences between the two, and they generate an index, and that index is called the Southern Oscillation Index, the SOI. The SOI is, when you have sustained negative values below normal pressure in Tahiti and above normal pressure in Darwin, that typically indicates an El Nino and are accompanied by a decrease in the strength of the Pacific trade winds. All right, so try to visualize this. I'll show it to you a little bit better. But if you have high pressure over Australia and you have to your east low pressure, high to low, that's going to oppose the trade winds. Water's going to warm up. All right. Whereas the opposite with sustained positive values, you have above normal pressure in Tahiti, below normal in Darwin. So now, instead of going from Australia to Tahiti, the air is flowing faster from Tahiti towards Darwin to Darwin. So now you have stronger easterly flow or stronger trade winds. And this is going to be an indication of La Nina that's accompanied by an increase in the strength of the Pacific trades. Okay. So I'm going to show you that here. Darwin's approximately here, Tahiti's approximately here, right? So if you're looking at this region, the Pacific, now again, it depends exactly where the warmest waters are, but keeping this basic, right? If you have high pressure here, low pressure here, high to low, that will oppose the trades, and that will cause warming of water or El Nino conditions, right? Now, if you reverse the circulation, you have high pressure more towards Tahiti, low pressure over Australia, high to low. That's just going to enhance the trade winds, faster easterly flow, more upwelling, and that's how you get La Nina. All right, so not overly complex, but still an important point to understand. Because this is important. While it's not the only piece, and people do probably give it more credit than it deserves, it still is an important piece of the puzzle. So here's today, actually, I pulled this up for July 1st. In general, I've always heard, especially the 90-day average, if you're at -8 or +8, you're either, -8 would be El Nino, +8 would be La Nina, right? So We maybe not quite. We're in that weak El Nino range right now. You see the 30-day average is over 8. The 90-day is getting pretty close. Our daily's been fluctuating up and down a little bit. There's a lot of debate whether we're going to stay in this El Nino or it's going to collapse. Different model outputs are showing different things. But regardless, even if the El Nino stays around, I don't think it'll be a very strong one. It'll be just a little bit warmer than neutral, maybe a weak El Nino. And you see that water pattern right now. What does this look like? Well, first, what's that? It looks like a what? A warm PDO. Not perfect. You have a little bit of cold here, but it's got that warm PDO look. And what do you have here? While it's not raging or anything, that definitely looks like more of what? An El Nino, right? So that's interesting. That's something to watch. But also, not to go on a tangent, but look at this here. You got warm, cold, warm. You get that unimpeded, rising motion towards the U.S. That's interesting. That's kind of that tripole look. So you got some things that argue maybe that it's not going to be the biggest season, but then you have other things that do argue that it is going to be a pretty good season. So it's a little tricky with this, but when I see that type of pattern with that warm, cold, warm, yeah, maybe the overall numbers are not going to be through the roof, but that concerns me later on in the year for maybe some landfall. So we'll see how that goes. And I'll show you later, too. We're in a negative NAO. So you can kind of see that pattern that's setting up for, I'm not going to say the numbers are going to be super high. You're not saying we're going to have 17, 18, 19 storms. But again, it's all about impact, right? So when I see that pattern, it does worry me a little bit. But focusing on the Pacific here again, warm, that's definitely got an El Nino look to it. But we'll see. This could easily collapse as we move on through the hurricane season. If this starts to cool off, that's really going to influence this. All right, so that's something to watch. All right, so I've talked a decent amount about this, but just a couple more slides. El Nino is anomalous warming of surface ocean water temperatures in the eastern tropical Pacific, accompanied by suppression of upwelling off the coast of Ecuador, northern Peru. It's called El Nino, which is Spanish for boy child, because its condition often occurs around Christmas. But that's not always true. I mean, you can have El Nino any time, any time of the year. Okay, so, but that's what it's named for. It can last for months, even weeks. And what I mean by that is, even if you have, let's say you have a La Nina going on, doesn't necessarily mean the whole time period is going to be a raging La Nina. You can have ups and downs throughout it, right? But in general, how long do these patterns last? They last at least usually about 6 months, and sometimes they can go a couple of years. It's possible, all right? So it can go over a year, and it can lead to extreme weather events over widely separate regions of the Earth. So what's going on in the Pacific can affect things way down the line. So here's some examples of different El Ninos, just to show you the differences. 1982, that was a very strong El Nino, but you can see where's the focus. It's more in the eastern Pacific, right? It's more of the classic look to it, okay? Whereas 97, it definitely still has that classic look, and it's definitely a strong El Nino, but do they look exactly the same? Let's focus off the west coast here. Yeah, there's warm, and it's still pretty good, but you can definitely see the 97, the water was warmer off of California, and you had more of a connection with that subtropical jet. You had more rainfall. Also, look at the Atlantic Basin. There's some differences there as well. So my point again, even when it kind of has that classic look, everything around it's not always going to look the same as well, okay? 2002, that does not look like the classic look. That the warmest water is more what? More in the central Pacific. It has more of a Modoki look, right? Especially as we go on, what's left, even though it's becoming neutral, has more of that Modoki look. And why is that important? Well, I remember this year well, and the El Nino was coming on, and a lot of times people associate El Nino, especially here in the South, with cool, wet conditions. And that generally is true. Some of our colder winters, and when I say colder, I'm not talking like lows in the teens, that type of winter. I'm talking a lot of El Nino winters when we have that more classic look like this. It's just cool, cloudy, rainy every day. 40s, lows in the 30s, just that nasty, cold, wet, uncomfortable, horrible pattern, right? But you don't have the big ups and downs. Well, that's what a lot of people were thinking this year, right, with this pattern. But you see how different that looks compared to that, right? And what was going on during the time was we had a negative NAO. So even though you had kind of a weakish El Nino that a lot of people thought were going to keep us while cool, wet, and nasty, not keep us bitterly cold and kind of suppress the snow, that negative NAO actually caused a huge block, which helped the troughs dig in. This influenced the moisture a little bit, and you got some pretty awesome nor'easters. The one in 2003, what people call the President's Day Part 2, that was a massive nor'easter, and a lot of people were not forecasting that. So, again, I'm just trying to show you there's differences. Every year is different. 2015, definitely more of that kind of classic look to it. Definitely a strong El Nino, similar to 82 and 97. But let's go back real quick to that again. Oops. Look how much warmer, even though it's warm along the west coast here, there's a lot more cold pockets, in the Pacific, whereas that does not look the same, right? So, again, kind of similar, but still differences, all right? So, I know I talk about this a lot, but no two are the same, okay? And you can see that progression as it, not progression. This is now currently, right? So this looks, obviously, it's much weaker than that, okay? All right, so La Nina, cooler than normal sea surface temperatures in the central and eastern tropical Pacific due to a period of strong increase in trade winds, opposite conditions to El Nino. La Nina is derived from the Spanish for girl child. Both El Nino and La Nina are extreme forms and fluctuations occur in the trade winds, all right? So we've talked enough about that. Here's some examples of La Nina. Just like El Nino, no two are the same. You can see the differences here. There's some similarities, but there's always some differences as well. There's overarching patterns with these, but they're not always going to be the same, okay? You can see 2011, that was a pretty powerful, strong La Nina. One of the stronger ones on record, 2010 and 2011. So let's see the progression of that 2010 La Nina. Definitely has more that cold PDO look, especially as we move out later on. And look at how classic of that cold PDO, La Nina. You see how they're feeding off each other. That's an amazing La Nina, right? They're not always going to look like that, okay? So what does that mean? Really strong trade winds, right? So if you have really, really strong trade winds and you got the westerlies opposing the trade winds, I talked about this before when we're talking about tropical forecasting, you're going to get a buckling of the jet with this La Nina pattern. Now, once you get the buckling, it just depends. Are you in the trough or are you in the ridge, all right? So with a positive SOI, if you're in the trough, you're going to be pretty cold, right? If you're in the ridge, you can be warm, all right? It just depends on where you are in the placement of that. And then just showing you that year, you can see how quickly it changed. It went from, El Nino to a La Nina pretty quickly. So they can switch. You can go from El Nino to La Nina pretty fast or from La Nina to El Nino pretty fast, all right? All right, so I don't want to spend too much time on this because I feel like some of this is overgeneralizations, all right? But in general, you have a more pronounced subtropical jet. You have an increase in the north to south temperature gradient over the eastern subtropical Pacific. Don't memorize this, too much. El Nino does usually enhance the subtropical jet, but it's not going to tell you exactly the placement. And again, each one's different. It just depends on where that warm water is. Okay. A lot of times in El Nino, you do have a gradient, and that's where you get that convection. But it depends if this water is really a lot colder than this water, right? So it really just depends on the setup. But in general, I don't think this is horrible. You do have more of an active subtropical jet with that gradient. So you have a strong jet stream and storm track, during the winter across the southern U.S. With fewer storms and mild temperatures across the north. Again, overgeneralization, but I put this here because you're going to read, if you read textbooks or you see things, you're going to see people talk about that. More west-east flow of the jet stream across the lower 48. In general, you do have a faster progression and a stronger subtropical jet, okay, in general. But again, it depends on where it's set up. So this is overgeneralization, stronger subtropical jet, wetter conditions in the west. But again, it just depends. I mean, if you have a negative NAO and you have a strong trough here, this may just feed into the trough and you get a lot of nor'easters, and it could still be cold. There's other factors involved in it. But in general, with all things being equal, faster subtropical jet, more wet, cool conditions this way. But again, no two El Ninos are the same. I've talked about this enough. You know that's more the classic El Nino, and that's more the Modoki El Nino. La Nina, you got more of absence of convection over the eastern half of the Pacific with the colder waters. That kind of makes sense. Deep tropical convection and deep tropospheric heating shifts more towards the western Pacific where the warmer water is. Reduction in the north-south temperature differences in the subtropical areas. So you get more of this type of pattern. But again, it's not always going to be exactly that way. No two La Ninas are the same as well. Okay, so you usually get more amplified flow over the U.S. during the winter with colder and stormy weather over the north and warmer, drier weather across the south. Now that's a real overgeneralization, but that part is true, right? Because if you have stronger trades opposing the westerlies, you do get more amplification. But where exactly that trough and ridge is, that's where it gets more tricky. Okay, if you had the negative NAO, then it'd be cold in the east. If you didn't, you could have a big ridge over you, right? It just depends, all right? So I'm not going to focus too much on that, but it's there because if you read in textbooks and you read literature, this is what you're going to get to see. I think we talked about this enough. Increased trades, you get that buckling in the jet, but the key is right here, variable, right? This is variable. Sometimes the high could be set up here and the trough could be in the east. So sometimes with the La Nina, you do have more meridional flow. You have more trough ridge, much more pronounced than El Nino. But where exactly it sets up is still tricky, all right? It could set up where you have a big trough over the west and a ridge over the east, okay? Now we're going to move into the Pacific Decadal Oscillation. We've talked about this a good bit. I think I can go through this pretty quick. The PDO concept was first developed in 1997. I talked about this with a man named Stephen Hare at the University of Washington while researching the relationship between Alaskan salmon and the Pacific climate. So he's looking at salmon migration and how the waters of the Pacific affected that, and they started realizing that it's not just using that for salmon migration and production and how that works. They could use it for weather, okay? So we talked about this a good bit. The PDO is more in a 30-year cycle, 20 to 40, but 30 is a good round number there, where ENSOs are more 6 to 18 months. And the effects are more evident in the North Pacific, North American region, all right? So we've really hammered this a lot in hurricane forecasting, so hopefully you feel pretty good with that. During a positive PDO, the waters in the central North Pacific are cool, and the waters along the west coast of North America are warm, okay, so positive, warm phase. The strongest PDO impacts are in the Pacific Northwest, but warm phase of PDO are created, or correlated, I should say, with more El Nino-like North American temperature patterns and precipitation anomalies. So we talked about that plenty, all right? Warm PDO, what does that look more like? El Nino, okay? So here's your warm phase. I've showed you that before. I've showed you this as well. Kind of has that horseshoe of warm, and it has what? More of an El Nino look to it. All right, so we've talked about that plenty. The negative phase, the cold phase, brings the opposite with warmer than normal ocean water temperatures in the central North Pacific and cooler waters, off the west coast. This is more La Nina. So again, I don't need to talk about this too much because we already talked about it so much. You see the cool water there. You see that horseshoe cold. And that has more of a La Nina look to it. There's still considerable controversy existed over how the PDO works and how it might be best monitored, modeled, and predicted. We talked about that also with when did we switch cold. There was arguments that it happened in 99. I kind of feel like it's more 2007. But in fairness, since 2014, we've had this warm spike again. So there's no way to know exactly for sure, at least not for probably another 5 or 10 more years, all right? My guess is right around 2007, but it's difficult. It definitely doesn't seem like this pattern is at least in this cycle, is easy to identify, all right? And it's important because considering the phase of the PDO may be critical, it is critical in predicting the effects of ENSO, all right? One thing to consider, especially with weather and just really anything, and it makes it really complex, but also at the same time is why I love the challenge of it. What we consider a long time as humans is not what a decadal oscillation considers a long time. So, if you live to 100 years old, that's a long life. In the world of weather or climate, 100 years is nothing. All right. So just keep that in mind. All right. There's a big difference on how we think versus how climate and weather works. Right. I mean, look at hurricanes. We just spent half of the class on it. Right. We really have data of hurricanes maybe going back to the late 1400s from the Spanish that came over with the fleet, and they were, running into hurricanes, and that was really some of the first observations of them. But what happened in the 1200s? What happened in the 800s? What happened, in the 200s? So that's my point. Like, we know some, but there's a lot of missing information. Okay. So we talked about that. It looks to me right around 2007, we're going back into a cold phase here. But there is still some argument on that because look at the last few years, it's really spiked back up. Some people were thinking 99, then we had that spike up and then down. So it'll be interesting to see what it does in the next 5 or 10 years. This is interesting. This is with research from NOAA. They were considering 99, but you can clearly see during the cold PDO, you get more La Niñas and less El Niños. During the warm, you get more El Niños, less La Niñas. Again, just because you're in a cold PDO does not mean you can't get El Niños, but you get more La Niñas during the cold versus El Nino, and you get more El Ninos in the warm versus the cold. All right, it's pretty obvious. And not just more, the duration in months is longer. So during the positive or the warm PDO, your El Ninos are lasting about 21 months on average, where your La Ninas are only lasting 12 months. All right, so the warm PDO, not only are you getting more El Ninos, they're lasting longer, you're getting less La Ninas that are shorter. But the opposite on the negative, during the cold PDO, less El Ninos that are shorter, more La Ninas that are longer, all right? And that's why really understanding the PDO is so important, because if you understand when these shifts are going to occur, you can kind of forecast the really long-term temperature patterns, right? Because if we truly are going into a cold PDO and it's really going to become pronounced the next 20 years and we have more La Ninas and colder water in the Pacific, what's that going to do to the area around it? It's going to cool everything off, right? Especially a body of water like the Pacific. However, on the flip side, if we don't really go into the cold PDO and it goes back warm and it stays warm, well, now what is it going to do? With all that warm water, everything's going to warm up, right? So it is important. It really is, not just for shorter term, but for longer term as well. Madden-Julian oscillation, we've talked about this a good bit. Roland Madden and Paul Julian discovered the pattern rising and lowering pressure that followed a 30 to 60-day cycle across the tropical Pacific Ocean. In more of a neutral pattern, I find it takes about 40 days. And it depends, again, going back to these water temperatures. Are we in El Nino or La Nina? Because this rising motion is going to like to hang out where the warmest water is, all right? And going back to what we just talked about, if the Pacific's cold and you have this imbalance, it's going to be made up for in the Atlantic. But on the flip side, if the Pacific's warm and you're getting plenty of this heat redistributed, probably not going to have as much activity in the Atlantic, right? So these all tie together. It really is important and really interesting how that happens. It's kind of cool, actually. So these atmospheric waves seem to rise up in the Indian Ocean and travel east across the Pacific, which is interesting. That's going against the trade winds, right? Trade winds are coming across the Pacific, east, right? And these are moving from the Indian Ocean towards the east. So that's interesting, right? These areas of convections are moving against the trade winds, all right? So you get areas of enhanced and suppressed convection. So here's a model of that where these pulses of energy are moving. You got rising motion, and then you got more suppressed convection. Either maybe this is oversimplification, but it kind of makes sense, right? Like you get like some sort of squall line that comes through, right? Well, what happens on the back of that squall line where all that rising motion is? You get a lot of sinking, subsidence on the back, right? So kind of like that. I know I'm oversimplifying it, but maybe that's a good way of looking at it, right? Pulses the rising motion, moving against the trade winds, originating near, in the Indian Ocean and moving across the globe. Between a 30 to 60-day pattern, but I found the neutral more like 40 days. But again, it depends where that warmest water is. If you have El Nino, it's probably going to hang out more in the Pacific. If you have La Nina, it's probably going to hang out more in the Atlantic. Studies have shown hurricanes are 4 times more likely in the Gulf of Mexico and the Western Caribbean during the rising phase, Talked about that plenty. But that, just because we're not in the rising phase, does not mean we cannot get hurricanes and powerful hurricanes. We have definitely had powerful hurricanes before when we're not in the rising phase. But when we are in 8, 1, and 2 especially, our chances really increase, okay? So that's a great example of that. Remember, this is neutral. The further out, the more rising motion. For us, we're 8, 1, and 2 is the octants or phases we're looking for. So again, I've talked about that plenty. I think you probably have a good understanding of that. And also, it's not just for where the rising motion is. Well, it is for where the rising motion is, but it's not just used for hurricane activity. It's also used more and more for temperature forecasting. If I know where that rising motion is, and I know where the sinking motion is, I have a good idea where my troughs and ridges are, which can help with what? Temperature patterns, right? Pattern recognition. North Atlantic Oscillation, NAO, all right? So we've talked about that a good bit, but we'll break this down a little bit more. It's a large-scale seesaw and atmospheric mass between the Bermuda Azores subtropical high and Icelandic polar low. The NAO is calculated based on weighted ratios of pressure taken in Lisbon, Portugal, and I'm not even going to try to pronounce it Iceland, all right? If you can pronounce that, more power to you. The index varies over a variety of timescales and to show a tendency to remain primarily in one phase intervals lasting several years. All right. So like a lot of these others, indexes and teleconnections, there seems to be longer decadal patterns with it. It's interesting. They're not always going to match up exactly. Remember, even the West African monsoon was going in decadal patterns. It's kind of interesting. Like I really feel as we learn more and more, we're going to see that these events occur in more of these larger time frames with, ups and downs throughout hundreds, thousands of years. All right. So it's interesting how that all works. So the positive NAO, we talked about this a lot. I think I even put this exact same slide in here in the hurricane lectures. So stronger than normal subtropical high and a deeper than normal Icelandic low, I should say. The increase in pressure gradient produces an increase in the frequency and strength of winter storms crossing the Atlantic on a more northerly track. Europe in general experiences warm and wet winters, while it's cold and dry over northern Canada. The eastern U.S. has mild and wet winter conditions. All right. So what do you not have? You don't have the block. You have faster progression. You have more storms, but probably not as pronounced, not as strong storms, more mild, wet conditions. Okay. And this is, a good way of looking at that. You don't have that block. Everything's progressing faster across the United States. You may have more storm systems, but you're not going to get that phasing, those powerful systems that go up the coast. You're not going to get the big nor'easters usually. It doesn't mean you can't, and it doesn't mean you can't get cold air, okay? You can still get plenty cold air with a positive NAO. It's just not going to lock in as long. It's not going to be as pronounced as if you did have a negative NAO. All right, so negative NAO, I'll let you read that. It's the opposite. And when they say, a weak Icelandic low, what's really the best way of saying that? High pressure, a block, okay? So the eastern U.S. receives more Arctic outbreaks and more snowy weather conditions, all right? So I've showed you that, and then this is a better representation. Here's that block causing troughs to dig further in. You get more phasing, you get more of a temperature gradient, you get bigger, nor'easters and stronger storms. You get that cold air that locks in longer, that pushes further south. This is how you get your coldest pattern setups, okay? The effects of NAO seem to be most pronounced during the winter, but it does impact weather during the other seasons. We talked about that. The negative phase of NAO has been linked to warmer than normal temperatures in the eastern U.S. during the summer. Why? Because if that ridge balloons out, it's going to expand down into the northeast U.S., and what does that do? That sets up what? Lowering pressure to the south, and if any storm forms, it's going to funnel the United States, all right? So there's definitely seems to be a link between the negative phase of the NAO and an increase in tropical activity in the Atlantic Basin. All right, so here's an example of the NAO, and remember we talked about this. Remember that 2003 or 2002, 2003 year where people were talking about an El Nino and how it's going to be a wet, cool winter, but not really a cold, snowy winter? Well, it was a cold, snowy winter. Why? Because the NAO was negative, and that El Nino was more of a Modoki El Nino, right? So that's where you got to be careful. I'll never forget that. So many people are like, oh, this winter is not going to be anything. El Nino, we don't have anything to worry about. Well, yeah, it was El Nino, but it was weaker, and it was a Modoki, and the NAO was negative, and that caused blocking, and then it threw more moisture into it, and then we got big nor'easters and cold and snow. Okay, so just be careful. You got to look at other things, all right? And even though the overall was negative, you do see some spikes. It wasn't like it was negative the whole time. There was some ups and downs in it, but overall you can see it was negative throughout most of the year there, at least the beginning part into the end of December into the winter. Currently, we've been in a negative NAO for a while now, and that will be interesting as we move into the heart of the hurricane season. If that El Nino doesn't really become pronounced and it weakens, and especially if, at the very least that El Nino moves more to the Central Pacific, and we have this blocking NAO, we have this big ballooned high, and we have that Atlantic tripole, I wouldn't sleep on this year. I mean, 2019 has some potential. Again, I don't know if the numbers are going to be super high, but I think there could be some definite impacts this year. Things are starting to kind of shape up that way, so we'll see how it works out, but it's kind of interesting. Arctic oscillation. All right, so we really haven't talked too much about this, but the good news is it goes really hand in hand with the NAO, okay? So the negative phase is associated with blocking in the Arctic, which allows cold Arctic air to spill south into the mid-latitudes. Thomson and Wallace found that when the AO is negative, temperatures on average are several degrees cooler than normal over most of the U.S., Northern Europe, Russia, China, and Japan. And this is when cities such as Dallas, Seattle, Paris, Tokyo typically have their coldest days. All right. So what is this really saying? When you have a negative Arctic oscillation, you have blocking in the Arctic region, which does what? It takes that cold Arctic air and pushes it from the Arctic region to the mid-latitude regions. All right. So it helps push that Arctic air out of Canada towards the United States. And it really does seem to go hand in hand with the NAO, right? When you have a big block of the NAO, right? Well, where do you think that Arctic air is going to go? It's going to go south towards the U.S. So a lot of times, not always, but a lot of times when you have a negative NAO, you're also going to have a negative AO because that Arctic air is going to come from the Arctic regions and move towards more of the mid-latitude regions. Whereas if you have a positive NAO, a lot of times you have a positive AO because there's no block, and that colder Arctic air is going to stay up in the Canadian region and not move towards the U.S. So they do seem to go hand in hand, all right? So not overly complex, but just something I wanted to add that you guys hopefully will be able to understand. And when you follow the weather and you see that, like if I see a negative NAO with a negative AO, I'm pretty confident cold's coming, okay? Now, it doesn't necessarily mean it's going to last for a month, but it's at least going to last for a little while. The longer that negative NAO persists, the stronger the block, the more pronounced it will be over time. Eastern Pacific Oscillation. All right, I'm going to briefly talk about this. I don't want you to memorize everything on it, but I just want you to understand the overarching idea, okay? So during a negative East Pacific Oscillation, all right, people call this the EPO, you have higher atmospheric heights, pressure, and temperatures in the Northeast Pacific and Alaska than the subtropical East Pacific from near Hawaii eastward. So what does that mean? It just means you got a big high pressure over Alaska and into the western U.S., all right? So during the negative EPO, when you have this big ridge in Alaska and the western U.S., what's gonna happen? It's gonna help do what? Push that cold down to the south, okay? Whereas on the positive, it's the opposite, okay? Higher atmospheric highest pressures and temperatures in the subtropical Eastern Pacific and lower highest pressures and temperatures in the Northeast Pacific and Alaska, all right? So during the positive EPO, you have a trough over Alaska and into the west and more ridging into the east, okay? Especially east of the Rockies, okay? So going back again, if I'm in a negative EPO, I'm going to expect more of a trough into the east, all right? Especially in combination with a negative NAO. If I have a negative EPO and a negative NAO, and I'm going to assume probably at that time you're going to have a negative AO, oh, cold's coming. Okay, it's coming. All right, you got a block here, you got a block here, you got unimpeded flow of cold coming towards the U.S., and that's a lot of times how you get that cross-polar flow. I talked about that kind of in the weather analysis section. You got a block here and a block here, and you get that air coming across Siberia and coming down the pole. That's how you get some of the coldest air you're going to get in the United States, okay? Whereas with the positive, opposite, right? Especially, look at this pattern. What is that? Does that look like a negative NAO? No, that looks like what? A positive NAO. So positive NAO, positive EPO. no block, cold's not coming, ridging in the east, positive AO. All right? And I'll let you read all this other stuff with it, but I just wanted to keep it simple. I know this is a long lecture, so I don't want to go too much more in depth with it, but just understand the overarching idea behind the negative and the positive. The Pacific North American pattern, the PNA, this is characterized by atmospheric flow in which the west coast of North America is out of phase with the eastern Pacific and southeast U.S. The positive phase characterized by deeper than normal troughs over the eastern United States and a stronger than normal ridge over the western U.S. This pattern is associated with mild than normal temperatures in the west and colder than normal temperatures in the east. So that makes sense, right? Positive PNA, what do you have? You have a stronger than normal ridge over the west, which is associated with what? Milder conditions, and a stronger than normal trough over the east, which is associated with what? Colder than normal conditions, all right? So, positive PNA, ridge in the west, trough in the east. Pretty self-explanatory, okay? The negative phase of the PNA is characterized by a trough in the west and a ridge in the east. So now the pattern's reversed, okay? Trough in the west, ridge in the east. Now you got warmth in the east and cold in the west, okay? Again, pretty self-explanatory. All right, so this is what we're going to end with. We're going to kind of put this together and tie it to the southeast U.S., all right? So we're going to look at prolonged periods of well below normal temps versus well above normal temps, all right? And these are more of the extremes, okay? So again, southeast U.S., colder than normal, warmer than normal, all right? We're going to look at the SOI, the NAO, the AO, the EPO, the PNA, okay? And this is something I want you to remember, all right? Because if you understand how the pattern's setting up, it's going to help you with the temperature patterns, okay? And it's going to give you a big advantage on that long-range forecasting. Okay, so let's focus first with the SOI. So during a below normal pattern, you're looking for a positive SOI. Why? Well, with the positive SOI, you get what? The faster trade winds opposing the westerlies, more of a buckling, all right? But then it depends on, remember it was variable, it depends on where it sets up. If you're in the trough, you're going to get below normal temps. If you're in the ridge, you're going to get above normal temps, all right? So the positive SOI can produce some of the coldest weather and some of the warmest weather here in the southeast U.S. It just depends exactly where you are. Are you in the trough or are you in the ridge? Okay, so hopefully that makes sense. Negative NAO, hopefully you got this by now. I feel like you should. A block in Greenland. Negative NAO means what? Cold air towards the eastern U.S., southeast U.S., all right? So negative NAO is going to lead to below normal, positive above. NAO and AO go together, so same thing. Negative AO will lead to below normal temps in the southeast U.S. and above normal temps typically in the southeast U.S. EPO, what are we talking about? Either a ridge in Alaska or a trough. If Alaska's warm, we're going to be cold here in the eastern U.S. or southeast U.S. It's as simple as that, right? So with that negative EPO, that big ridge in Alaska, warm conditions in Alaska, that's going to lead to cold conditions here in the southeast U.S. And with the positive EPO, it's the opposite. You'll have cold and a trough in Alaska and a ridge and warmth over the U.S., all right? And the PNA is just one you're going to have to memorize and just remember. It's kind of it's more descriptive than the other ones, but a positive PNA, ridge in the west, trough in the east. Negative PNA, what do we got? Opposite. Trough in the west, ridge into the east, okay? So again, I try to tie this together. I know this stuff's complex to a point, but I try to my best to explain it the best I can. I try to incorporate the other parts in the class, so hopefully everything is kind of tying together. Just like always on the quizzes, I'm not going to nitpick certain things. I'm going to find main concepts, all right? So you should be fine with everything. But, of course, if you have any questions, let me know, and I will help you the best I can. And, again, I know this was a longer lecture, but hopefully you broke it up if you wanted to. And if not, you went through the whole thing. You found it interesting. And, again, if you have questions, just let me know. And when we move into lectures 8 and 9, they'll definitely be a little bit shorter, okay? All right, so I'll be back with lecture 8.